Welcome students. We want to discuss about derivatives and integrals of vector functions. Before we start, let's see this beautiful quote by David Hilbert. So Hilbert was one of the influential and I would use the word biggest mathematician of his time. He has many results in algebra, number theory associated to him. One of the So he has list of 24 problems, which some of which is still unresolved. For example, Riemann hypothesis is one of them. Anyway, so let's read the quote, which says, mathematics knows no race or geographical boundaries. For mathematics, the cultural world is one country. Yeah, quite a beautiful quote. So coming back to the derivative and integrals of vector functions, let's recall what is a vector function. So a function that associates with the number t, the vector r of t, is called a vector valued function. So essentially, your vector function is a function from some real numbers, some subset of real numbers to a vector. So it could be v3, space of space of three-dimensional vectors, or four-dimensional vector, or two-dimensional, or it could be to v2, it could be to any n-dimensional as well. But in our course, we are restricted to v3 and v2 sometimes. Okay. So we want to do the calculus with vector valued function. So for calculus, we have to define. So we have to see what does it mean by a limit of a vector valued function? What does it mean by a vector valued function to be continuous? What does it mean by a derivative of a vector valued function? And what does it mean by integration or integral of vector valued function? So these are the few things we should see if we want to understand uh, the calculus of vector valued function. Although this list is not complete, but these are the first few things we should see. So what is a limit of a vector valued function R? So vector valued function R is given by component f, g, and h. So these are the functions. So we have R of t equals to f of t, g of t, h of t. So this is our vector valued function. Now, what does it mean by limit as t goes to a of R of t? Now, this is defined by, so this is a definition. This is same as limit as t goes to a f of t, limit as t goes to a of g of t, limit as t goes to a of h of t. So, and this limit is t goes to a of R of t is this limit provided it exists. Provided these limits exist. So again, the idea is you're defining the vector valued limit of a vector valued function based on these individual limits of each component, and that we already know how to compute using calculus. Okay. So let's do an example. Let R of t be sine 2t by t, 1 plus t, and t squared plus t, and let's compute quotient. So let's compute limit as t goes to 0 of R of t. So this by definition is going to be limit as t goes to 0 of sine 2t by t, limit as t goes to 0 of 1 plus t, and limit as t goes to 0 of t squared plus t by t. Yeah, now we have to find out each of these individual limits. So that we can do in the following way. So this is going to be a limit as t goes to 0, sine of 2t by t. Now we multiply and divide by 2. Here we can take the limit directly. As t goes to 0, we'll get that to be 1. And here again, we should take t common. So we have t plus 1 upon t. So this is going to be, this limit is 1. So we get 1 times 2, which is 1. Here you'll get 1. And t cancel out. When you put t equals to 0, you get 1. So limit as t goes to 0 of r of t is this. Now, what does it mean by continuity? So continuity r of t is continuous at a if limit as t goes to a of r of t equals to r of a. And r of t is continuous on I if r of t is continuous at every point on I, that is f of t, g of t, and h of t, that is f is continuous on I. So this is the idea behind continuity and the limit. Now, the key thing to observe is that limit is done component wise. Are taken component wise. Okay, so this is an important idea, that you're doing things component wise. Now let's move on to the next part of the discussion. This is about continuity. Sorry, this is about differentiability. We want to talk about derivative. So I'm going to use a slightly different format of r of t. Now, instead of using f, g, and h, let me call the components as x component as x of t, y component as y of t, z component as z of t. Yeah. Then the derivative of this vector valued function dr by dt is r prime t, which is given by limit as h goes to 0, r of t plus h minus r of t over h. So this is what the definition of the derivative of a vector valued function is. Now, what is really happening is as follows. So you have r of t. You want to compute the derivative at point P, whose position is given by r of t. So what you do is you take you take, this is corresponding to t, then you take r of t plus h, which corresponds to point q. So this is so position vector of q is r of t plus h. So their difference is given by pq, which is r of t plus h minus r of t, following the triangle law of vector addition. Yeah, so you can see that these arrows, so that now if you divide this by h, if you divide this by h, then you are basically taking some vector which is parallel to this vector. So r of t plus h minus r of t is some vector. You can still think about it as pq divided by h as basically going in. It could be this vector pq, right? Now what happens is the following. As you let h go to 0, the same thing will happen what happened when you were looking for the in one-dimensional case. So as you go 0, this secant will slowly become the tangent, right? So we get r prime of t is basically, that's a physical interpretation of it, that r prime of t gives you the tangent vector r prime t. Okay. So this is what the physical interpretation of it. Now the next question is, how do we compute such a thing? So how do you compute the derivative? So for that, we'll have the following. Let's take, so again, if r of t is f of t, g of t, h of t, then we have r prime t is f prime t, g prime t, h prime t. So let's come to this formula. So again, the idea is, if this is r prime of t is going to be f prime t, g prime t, h prime t. So let's prove this. So we have r prime of t is going to be limit as delta t goes to 0, r of t plus delta t minus r of t over h, or sorry, over delta t. Now note that I'm using h here, so to avoid the confusion, I'm using, instead of h, I'm using delta t. Yeah. So otherwise there's no difference between the previous one and this one. We can't use the same variable at both the places, right? Same symbols. So now let's compute this. This is going to be limit as delta t goes to 0, f of t plus delta t, g of t plus delta t, h of t plus delta t, minus f of t, g of t, h of t, the whole divided by delta t. Now I'll subtract the components. So let's subtract them. So we get equal to limit as delta t goes to 0. So now the subtraction of vectors is done component wise. So we have f of t plus delta t minus f of t. This is the first component. And then the delta t is dividing all the components. So let's just give it to the first guy as well. So this is the first component. Second component is h of t plus delta t minus h of t over delta t. Now limit as delta t goes to 0, this component, so limit will jump inside, right? So let's just do that as well. So this is going to be limit as delta t goes to 0 of f of t plus delta t minus f of t over delta t. Similarly, limit as delta t goes to 0, g of t plus delta t minus g of t over delta t. And then the next one is h of t plus delta t minus h of t over delta t, and then there is limit in front of it, limit as delta t goes to 0. Now we identify these limits to be f prime t, g prime t, h prime t. So this is how you compute the derivative. Again, the important key is derivative is done component wise. So derivative is done component wise. So vector valued functions, I mean, a lot of it is basically, I mean, you can do it component wise, right? So that's the nice part of it. So now in this case, we can find out what is r prime of t. So r prime of t is given by what is derivative of cost? So component wise, so first component derivative is derivative of cos t is minus sine. So minus sine 2t times 2. Now derivative here would be done using product rule. This is a second component t e to the power t, which is t e to the power t plus e to the power t times 1, product rule in that component. What about the next one is going to be using quotient rule. So t to the power 4 t squared times 1 by t minus ln t times 2t. So this is your derivative of r prime t. Okay, so now that derivative is done, we should go back to the physical significance of derivative. So derivative was slope of the tangent line in function of one variable. So it should serve a similar purpose here. Instead of slope, we have direction here now. So that is in two-dimensional. So from 1D, we had slope is replaced by 3D, or 2D is replaced by what? Direction. Okay. So, and the direction of line, right? I mean, if you remember, if you have R0 plus dV, this gave the direction. So let's repeat the same thing here. So we call r prime t as tangent vector to the curve C at point r of t, provided that r prime of t and exists and is non-zero there, right? So that's the idea, that if r prime t exists and is non-zero, then we call this as a tangent vector. Why do we need it non-zero? Because otherwise we'll have no direction if it is zero, right? So r prime t should not be zero to be called as a tangent vector. So now a tangent vector to curves to C at point P is a line passing through P and is parallel to R of t. So again, let's go back here in this one. So at P, if you want to find out the tangent line, the most reasonable way to look at this would be, it is basically, so it's basically this line along r prime of t. Yeah, so let's just draw that. So it will be essentially this line passing through P, which has direction R of t. So this will be the tangent line. Yeah. Okay. So let me erase that now and go back to our discussion. Okay. So a tangent line at P, and P's position of P is given by some point, say so you have R0. This will be given by, this is your position vector of P. So you have, say, point P, whose position vector is given by R0, and then you have this R prime, say this guy is given by R of T0, suppose the position vector of, so position vector of this point is given by R of T0. So this guy's position vector is R of T0. So, and then if this is your R prime of T, then the tangent line can be given by R of T0 plus T times R prime at T0. T times R prime at T0. Yeah, so this will be the tangent equation of the tangent line, vector equation of the tangent line. Tangent line. So this is a vector equation of tangent line. However, it's customary to use the unit tangent vector. So what is a unit tangent vector? So unit tangent vector is R prime of t divided by length of R prime. So basically you take a tangent vector, which is R prime t, and divide by its length. Then you get a unit vector. And so this vector is called unit tangent vector. Now let's embark on the following. Find the parametric equation of, of the tangent line to the helix R of t as I cos t, j cos sin t, and tk at point P 1, 0, pi. So first of all, we need to find out R prime of t. So R prime of t, so we have R prime of t equals to derivative of cos t is minus sin t. Derivative of sin t is cos t. And derivative of t is 1. First of all, and then secondly, we need to find out what is t0. Yeah. So we have R of t0. So R of t0 is going to be, on one hand, it is cos of t0, sine of t0, and t0. And on the other hand, it passes through the point P. That means it is going to be this. So therefore, t0 is what? If we equate, instead of solving these guys, we can directly look at the third component. T0 is what? T0 is pi. So T0 is pi. So T0 is pi. So therefore, equation is, so vector equation is R of t equals to R of t0 times t times R prime of t0. That is going to be, so t0 is pi. So we already know what is R prime of t0. It's going to be minus 1, 0 pi and plus t times. Now, what is R prime of t0? So we should, so, and here we should compute, and R prime of t0 is substitute pi. So this is going to be r prime at pi, which is going to be, you substitute in the derivative, so we get minus sine pi cos pi 1, which is going to be sine pi is 0, cos pi is -1, and 1 is 1, of course. So we get 0 minus 1, 1. Use the same color. Right, where t belongs to r, of course. Right, all different t's give you all the points, all the position vectors of the points on your line, tangent line. So therefore, what about the parametric equation then? Parametric equation is simply, this is going to be x, y, z. So therefore, x, so the parametric equation is x of t equals to -1 plus t times 0. Well, let's just write it down. Y of t equals to 0 minus t, so minus t, and z equals to pi plus t. So this is a parametric equation of the tangent line to the helix passing through these points. Okay. Now we have a definition of what is called a smooth curve. So smooth curve is a curve given by vector function. So all the curve in 3D are given by a vector function. So smooth curve is given by a vector function r of t on interval I, and it is smooth if r prime t is continuous and r prime t is not 0 on I. Yeah. So determine if the curve given here is smooth. So what do we need to decide? We need to see if r prime t is continuous and continuous, and if r prime t is not 0 on I. Here I is not given, so we'll consider the whole domain. So here I is equal to, that is, your I equals to r. So let's first compute r prime t. So r prime t is going to be 1 plus, sorry, the derivative of 1 is 0. So you get 2t minus 2t cosine of t with a minus sign. So what happens is, now r prime of 0, you can see, is basically 0, 0, 0, right? So first of all, this is continuous on R, right? Because each component is continuous on R, therefore the whole vector is continuous on R. However, we have r prime of 0 is 0. Therefore, this function, this curve is not smooth on R. However, let's restrict our attention. So this is case 1, 1. So let's ask the same question. If we have B I equals to, say, you just remove 0, say 0 to infinity. So let's see if it is smooth there. So first of all, again, r prime of t is 2t minus 2t minus sine t is continuous on 0 to infinity, and r prime t equals to 0 vector if what 2t minus 2t and sine t, each the component is 0. So this is 0 on I if 2t equals to 0, minus 2t equals to 0, and okay, so let me be slightly more refined when I'm saying this. So I want to say that it does not become 0 at any point, right? So how do I say that? Well, 2t is not 0 on 0 to infinity, right? Therefore, r of t, r prime t is not 0 on I, right? Because if one of the component is non-zero, then the vector is non-zero, right? So this is not 0 on I, therefore r of t is smooth or smooth on 0 to infinity. Okay, so it's not smooth on all real numbers, but it's smooth on 0 to infinity. Similarly, you can see similarly on minus infinity to 0 as well. So 0 is the point where the smoothness is lost. So if we consider an interval which does not contain 0 or contains 0 as the endpoint, you get a smooth curve. Now there are few rules of differentiation. They are very similar to the rules you had in calculus of one variable. So u of t plus v of t, if you want to take derivative of that, that is same as derivative of the first vector, that is same as d by dt of u of t plus d by dt of v of t. Now note that we had this discussion, the bold letters are the vectors. So when I'm writing it by hand, I'll put an arrow, but when I'm printing it, it will be given by the bold letters. Similarly, constant can come out, so c times u prime of t. Now this is a product rule. Note that f of t here is a real valued function. So there are three kind of products really. One is scalar multiplying a vector. One is dot product of two vectors. One is cross product of two vectors. And we need a differentiation rule for this different kind of products. So first one is you have f prime t ut plus f of t times u prime t. So it follows the similar rule, product rule. The only thing we should be careful about is that ut is and u prime t is a vector. Similarly, if you take the dot product of two vectors, u of t dot v of t, that is same as u prime t dot product with v of t plus u of t dot product with v prime of t. The same thing happens for the cross product as well. So u of t cross product with v of t is u prime t cross product with v of t plus u of t cross product with v prime of t. We also have the chain rule. So now if you're looking at the chain rule, your inside function should be scalar, right? Because u is a vector valued function which takes a scalar in. So if you want to take d by dt of this is same as u prime f of t multiplied by derivative of inside, which is a scalar function, so f prime t. So this is how we take, these are the differentiation rule for vector valued function. Yeah, you cannot divide one vector by the other, so that is not in the list. Now we define the derivatives, so we can define the integral as well. So integral, you can prove this using the Riemann sum idea. So we have integral, if you have given r of t as f of ti, g of tj plus h of tk, or by f of t, g of t, h of t. You can use either of these notation. So integral a to b r of t is given by, you take the first component keep it in the first component. G of t is, again, the second component will be integral of g of t dt. And third component is integral a to b h of t dt. So this is how we compute the indefinite integral. So now, again, the rule remains the same. So the idea is integral is done component wise. Yet again, okay, so let's look at the following problem. So let's look at a problem, namely, suppose you have r of t, so problem. So you have r of t equals to, let's take back what we had here, 1 plus t square, 1 plus t square, 1 minus t square, and cos t. So if we have r of t equals to this, problem 1, find integral of r of t dt. Now this is an indefinite integral. So indefinite. So then this is going to be 1 plus t square dt, 1 minus t square dt, cos t dt. So this can be seen as so what is the integral of 1 plus t square is going to be t plus t cubed by 3, t minus t cubed by 3, and integral of cos t is sine t, but each of them will have a constant of integration. So this one will come with plus c1, this one will come with plus c2. So I can write this as plus c1 plus c2 comma plus c3. So in principle, I can write this as the integral plus a vector c directly, where c equals to c1, c2, c3. Yeah. So this is the indefinite integral. Now suppose we are asked about a definite integral. So of course you can find c if you're given r, value of r at some point. Now suppose we have 0 to 1 or 0 to pi of r prime t dt. In that case, we'll get t plus t cubed by 3, t minus t cubed by 3, sine t, the limits are from 0 to pi. Now note that we don't add constants here, because in definite integral, you take any antiderivative and then substitute the limit. So here also you can think about a fundamental theorem of calculus for vector valued function. So let's substitute, we get what? We get pi, so upper limit minus lower limit. So pi plus pi cubed by 3 pi minus pi cubed by 3 sine pi. Then you substitute the lower limit, which is going to be 0 plus 0 cubed by 3, 0 minus 0 cubed by 3, sine of 0. So this turns out to be pi plus pi cubed by 3, pi minus pi cubed by 3, sine pi is, well, 0. So this is how the integral of vector valued function is done. Okay, very similar to the integral of real valued function. Only thing is that things are done component wise. So the major one of the basic rule is, so let's make that clear. Basic rule, everything is done component wise. Okay, so thank you for your attention.